But what we want to do here is that we want to go through examples 1.3, 1.4, and hopefully 1.5 with a little bit of conceptual stuff. So what I'm going to go do here is that I want to go and start on those chapters right now. Okay, so what you're seeing here is that you're seeing my screen here where I'm looking at example 1.3. And this is essentially the experiment that sort of like put the nail into the coffin for only thinking in Newtonian terms. And it really solidified relativity in a way that nothing has ever done before. So let's look at this question here. So it says you have muons. They're a subatomic particle, and they're produced several miles above the Earth's surface as a result of collision of cosmic rays. So typically what I'm thinking about here is that I have some atmosphere. Okay, so this is atmospheric particles. And what typically happens is that you get in, a proton comes in from outer space. It's a cosmic ray. So as this proton comes in, it's going to collide with the nitrogen and oxygen in the atmosphere primarily. There's some other things, but for the most part, it causes some type of interaction. So now that you have this interaction here, what you find here is that then you get a shower of particles. And one of these particles turns out to be a muon. And this muon is actually a negatively charged electron. And what do I mean by that? It's a heavy partner of the electron. So it has all of these same identical traits as an electron, but it has more mass. And that was a really, really big question for years and years and years. How is the muon really different than the electron other than its mass? And the answer is, it's not. It's almost identical. But because it has a bigger mass, it turns out that it has a bigger phase space in order to interact with the objects that it interacts with. And so what happens is that these guys start raining down. And what we find here is that these guys are moving pretty fast. So now I have these muons that are raining onto the surface of the Earth. And the first experiment was with Mount Washington. And then later experiments, it started happening with balloons. But the Mount Washington experiment is the original one. So if you go to New Hampshire, they have this mountain. And up at the top of the mountain, what they did here is they put a detector. And this detector is real easy to build. And the reason why it's easy to build here is because you're essentially detecting electrons. We're experts at detecting electrons. And so this detector at the top of Mount Washington, I'm going to call detector number 1. Why 1? Because that's essentially what the muons see here. And what they know about this guy here is that it's 6,000 feet high. And this guy in meters is 1830 meters. We only care about meters, not care about feet. And so as the muons come down, what you're going to see here is that there's a second detector. I'm going to call that detector number 2. So here we go. So the picture is that we have these detectors, and what they're essentially doing here is that they're going to detect the number of muons at detector 1, and then they're going to compare the muons at detector 2 here. So the whole goal here is that you want to compare the number of muons at detectors number 1 and number 2. So remember, 1 is at the top of Mount Washington. 2, this is at the surface of the Earth. Okay, so that's what we're doing. Now, what we want to look at here is that it turns out that the proper time of a half-life of a muon is 1.5 microseconds. What do I mean by that? So what that means here is that if I have a muon that's going through space, right? By the way, I just said something very not RC. We just have a muon that is moving. Doesn't say it's moving relative to me, but in the frame of the muon, it's not moving, right? So when I write that minus sign right there, I'm saying that this is a muon. So if I have a clock now, okay, so this is the proper time of the muon. What do I mean by that? That means that the muon is moving at beta, the clock is moving at beta, and so when we measure these two simultaneously, we get a half-life of what? 1.5 microseconds. Okay, so what do I mean by half-life? When I say the word half-life, that implies that I have a radioactive particle. And the half-life essentially tells you that these radioactive particles, that they decay exponentially, and that they decay exponentially. What that really means here is that they follow the radioactive or the radiation law. So they decay exponentially and follow the radiation law. And this radiation law, you probably, if you've taken differential equations, it's a very common thing in differential equation courses to actually derive, but it essentially says that if you want to know how many particles you have that are radioactive, it's what you started off initially with, and then you get a term called 2 to the n. And that 2 right there is really about the half-life. That means if I start off with 10 particles, after how much time do I end up with 5 particles? The time between going from 10 to 5 is the half-life, and that's where that 2 really comes from. And I'll explain a little bit more detail on here. So what we're seeing here is that if I now go back to our problem, initially at 6,000 feet or 1830 meters, they're going to measure this, what I'm going to call this the number of particles of Mount Washington, and I'm going to compare them to the number of particles at the surface of the Earth. So when I look at this radiation law, what I'm really looking at here is that I'm saying that if I detect this number of particles at detector number 1, by the time I get to detector number 2, if these guys are literally radioactive, they have to follow this radiation law right here. So that means what I really got to do is I got to say, so the number of particles that I'm going to detect at Earth's surface is related to the number of particles that I have at Mount Washington, at the top, of course, divided by this 2n. That's what the radiation law tells us here. And I'll get to a little bit more detail of what actually happens. But one of the things that we want to talk about here is we want to talk about this little n value here. So this little n is actually equal to the number of half-lives of the muon. And what we mean by that is that we know that if we have an observer on the ground versus another observer at the top, the observer here at the ground is going to do what? They're going to see time dilation effects. And because they see time dilation effects, we know that that 1.5 microseconds, the proper time of the muon, is going to be time dilated. That means it's going to last longer as it goes from the top of the mountain all the way down to its base here. So picture-wise, there's two pictures that we could think about. So if I think about these pictures here, I could imagine that I have a muon coming down. So what do I know about the Earth? The Earth is stationary. So in this frame here, I'm going to call that my S frame, and the muon's frame, I'm going to call this the prime frame. That's a totally legit way of looking at it. And by the way, that's exactly how I'm going to look at it in this problem. But there's a second way that I can look at this, which is absolutely correct. Or I could have the muon stationary, right? Here's my muon. I could have that the muon is stationary. And this time, what's happening? There's a relative velocity. So the top of the mountain and the surface of the Earth is going up instead. These two frames are what? They are equivalent. I can't tell the difference between this picture on the right and this picture on the left. Both of these pictures are correct. Let me ask you this here. If I drop a book on, towards the Earth, towards the surface of the Earth, we typically ask that silly question where, who applies a greater force? The book on the Earth or the Earth on the book? And according to Newton's third law, we say they're all the same. But do you really believe that? That the book is attracting the Earth? And you could probably say yes. It's just that the mass of the Earth is so huge that, its acceleration is, you can't really tell the difference. But at the same time, what you're finding here in relativity, that I'm using that as an analogy, in relativity, you might be saying, but this isn't about the force of gravity. Is really the Earth moving towards the muon? Isn't it the muon that's moving? And the answer is, you cannot make that statement. The principle of relativity says that you cannot tell the difference between the two frames of reference, so therefore both are legit. Very counterintuitive. So then if I start to move on here, and if I want to get the number of half-lives, we know that the number of half-lives, the way it's going to be here, it's going to be the time for muons to reach Earth's surface. So it's the time to go where? From the top of Mount Washington all the way down to the surface of the Earth. That's what I mean to reach surface, from the top of the mountain. And then at the same time, what we have to worry about here is the other one is that this has to be the half-life of muons measured relative to Earth. Because we know that the little green observer here, that little green observer measures a time-dilated muon. It's going to be longer than 1.5 microseconds. So that means the number of half-lives, instead of increasing, is going to decrease because of the time dilation. So physically, we expect this little n, the number of half-lives, to actually decrease for an observer on the Earth. So if I look at that thing, then let's look at the notation here. So what I'm going to do here is that here's my notation. If I'm talking about time, I'm going to use a little t. Okay? And so this is how much time it requires the muons to go from the top of the atmosphere down to the bottom. Now, if you look at the time dilation, or we're going to have time dilated half-lives. So what I'm going to do here is that I'm going to write this as a half-life. So this tau here and by the way, that's universal language for half-life, is a tau. But this time, we're going to measure it relative to what? Earth, not in the muons frame. So what we expect here is that this guy is going to be what? Of Earth should be larger than the half-life measured relative to the muons, the proper life. Right? We expect that because that observer sees the muons moving relative to him, so therefore we expect that to be larger. And this guy here is what we call little n. So in order for me to calculate the number of muons at the top here, I have to sort of like look at the whole thing here. So here's what we need here. So to get the number at the top of Mount Washington, you could see here is that I need what? I need the number of particles at the Earth. Well, I know they tell us that this is what? 400 particles per second, I believe, is what they're getting. Right? Or no, 400 muons per 1 hour. So we're given that. And we need little n. So that means in order for me to get little n, I got to get the time it takes for the muons in the Earth's frame to go from the top of Mount Washington to the detector, and then I need to measure the time dilated thing here. Right? So to get n, so that means we need, the first thing that we're going to need is we're going to need delta t of Earth And this is the time required to go from detector number 1 to detector number 2, right? In the Earth frame, of course. And the other thing that we need is we need the half-life. So this tau, 1/2 of Earth, while this guy here is the time dilated half-life. Right? Relative to Earth. So I need those two things here in order for me to calculate little n. Once I have little n, then I could calculate what the rest is here. So let's go calculate these guys then. So what you're seeing here is that now, so I want to go calculate delta T Earth. Right? This is the one I want right here. So let's go calculate that guy. So the first thing that I want to do here is that I want to remind you of the picture here, right? So the first thing that I see here is that when I look at my detectors, right, here's number 1, here's number 2, we know that the distance in the Earth's frame is that this distance in the Earth's frame, we said was 1830 meters, right? That's in the Earth's frame. In the Earth's frame, we know that the muons have a relative velocity. Maybe I should write this as beta. So we know in the Earth's frame, they're moving at that beta value. Because not only do the muons see that, but so does the observer on Earth here. So that means, I don't know what just happened. So what this implies here then, that the relative velocity equation then tells me that if I look at the Earth's frame, it's going to take me, that distance over time to travel that relative velocity. Or if I look at what? I can look in the muon frame. Or I could do this. So this is in the muon frame of reference, but since I don't have all those details, I'm not going to look at that. I'm only going to focus on the Earth here. So then you could see here, I could then determine delta T of Earth. And if I look at that, I get delta T of Earth is then going to be just the algebra over this relative velocity v here. So if I look at this thing here, then this is going to be what? I know that the distance is 1830 meters. I know that the speed is 0.995 c. So therefore, this tells me here that c delta T of Earth is then going to be 1830 divided by 0.995, and then I get a distance of 1839 meters. So I've calculated the first part of little n. Okay, so now I want to focus on the second part. The second part is I want to go calculate the half-life, the dilated half-life. So now I'm going to come in and I want to so this is the second part that I want to focus on right there. So now, here we go. So we know that standing on the Earth, muons are dilated. Why are they dilated? They're moving relative to us. Okay? They're moving relative to us. So then what that means here is that if I go and I look at my gamma factor, this is 1 minus beta squared, and then this will be 1 minus 0.995 squared, that this value that I get here, I get 10.01 for my gamma factor. So therefore, this tells me that in the frame of the muon, the Earth is going to, here, let me be careful here how I say this. I want to be RC here. So if I look at the time dilated muon relative to Earth, then that means I'm getting in the muon's frame, the proper time of the muon, to an Earth observer, it's going to be dilated, so I got to put my gamma right here. So in essence, this is the one that's the prime, this is the one that's the unprime. Why? Because if you go back to my picture over here, where is the observer measuring the half-life? Right there at the surface of the Earth. So they're making that measurement. And so when you look at that, you could see that this guy's really just multiplying this thing times 1, and this will give me 15 microseconds as measured relative to the Earth. Now, what's important about this here is that physically it has to make sense. You could see that because of that gamma factor, this implies that they last 10 times longer. Right? The relativistic factor tells us that the muons last 10 times longer. So now I have everything. So this tells us this is what we expected due to time dilation. So now the next thing that I want to do then is that I want to go calculate little n here. So now I want to determine little n. And it's the last piece to the puzzle effectively. So then little n, so remember this is the number of half-lives and this is going to tell me how much time did it take the muons to travel from top of Mount Washington to the base, and then this is the number of half-lives measured relative to Earth. So then I'm going to get, so look, I have a little confession here. If I put C here, that has units of distance. If I put C here, that has units of distance. So the way I had written it, there was no equal units here. So now they're PC here with this thing here. So then I got to write 3 times 10 to the 8 meters per second. That's for the speed of light. We saw that the time measured is 15 microseconds. And I'm going to divide that into what we just calculated a moment ago, 1839, and I get a value of 0.41 for little n. So now I have little n, and so now I could go in and I could just start moving around and calculating the number of particles detected here. So if I move this up just to conserve space, I'm then going to come in and I could write the following thing. So the first thing that I'm going to write here is that now that I got that, then this means here from the radiation law, I'm seeing here that if I have the end of the Earth, and this is the end and measured at the top of Mount Washington, because we're talking about that, then that tells you then that the number at Mount Washington is going to equal to what? The number on Earth, and we saw that this was 40 per hour. And then if I bring in my time factor, my half-life factor, I get a value of 531 hits per hour. And that gives me the number for Mount Washington. Okay. Any questions on this?
So, the whole point of this whole experiment was to see the speed and the cosmic decay of these sort of muons, or like I'm not.
Yes. This experiment was looking at the decay rate of these muons. And the thing that's really beautiful about this experiment is that it really nailed the coffin shut as far as whether special relativity was a viable theory for describing, like these fast-moving muons. By the way, just to show you that, special theory of relativity is really radical. I mean, it's so radical that the general theory of relativity was actually experimentally shown to be more valid than special relativity. This experiment happened in the 1940s. Einstein put his stuff out in 1905. So we're talking like 35 years or more before they could really validate it. Even though there was a lot of reasons to think that it was true, but it was general theory of relativity that, he put it out in 1915. By 1919, there was the guy who did the measurements in Africa. And even then, by the way, if you look at the error bars for the African measurements of general relativity, oh my gosh, they're horrible. I would say that they did not verify it at all. But everybody published in the papers and said, oh, Albert Einstein's the smartest guy to ever live. I think that's debatable. I think Newton has to be the smartest guy that ever lived, as far as I can tell. But that's a different story. But the fact is that this was the thing that, without any doubt, people came back and just says, there's no way special relativity is wrong. And like I said, now particle detectors do it zillions and zillions of times per day. And so, yeah, it's shocking to some people, but it's more tested than Newton's laws, which is just shocking to even think that. But it's the truth. Moving on. Let's go to this next one. I love this question. This is a really good question. And the reason why I like it is I think it's deep. And another reason why I really like it is that I think a space-time diagram really makes a difference between understanding this or not understanding this. And I think it brings in Lorentz transformations or Lorentz boosts here in ways that you really haven't seen used physics-wise. Like, you have problems 1.1 and 1.2 on your homework, but it doesn't really, that was just so that you go through sort of like the steps of how to use them. The real shit is right now. This is how you use Lorentz transformations that actually do physics for you. And you couldn't do it any other way. Okay, let's go look at this thing here. So this is a beautiful example, I think. I think this is a very sexy example for special relativity, no doubt about it. And it says, elephants have a gestation period of 21 months. Suppose that a freshly impregnated elephant, I'm assuming that's none of you guys, is placed on a spaceship and sent toward a distant space jungle at beta equal to 0.75. If we monitor radio transmissions from the spaceship, how long after launch might we expect to hear the first squealing trumpet of a newborn calf? Okay, so what am I going to do? I'm going to start with the graph or a picture of the situation just to make sure we're all speaking the same language here. And then we want to hit the space-time diagram. Space-time diagram is super clear in my opinion here. And I think it's indispensable in explaining what is actually happening here. Okay, so let's look at this thing here. So the first thing that I want to do here is that I want to start with the diagram. So we want to draw a picture of the situation. And so, of course, if we start going and doing the same type of picture that I've been drawing all along, right, here's my frame as observed by the Earth, of course. And then, of course, now we have our little rocket. And this rocket is moving relative to the Earth. So we know that they're moving at 75% the speed of light here. And of course, in this frame is where the elephant is at. So as this guy is moving, we know that this must be the prime frame right there. Now, if I think about physics-wise, of course, the elephant is going to have its time digestion, ooh, that came out pretty, dilated. So in this frame of reference, right, in this frame, what we know here is that the elephant does not move. Okay? And how long does it not move for? Well, for starters here, there has to be some type of time, the gestation period, that it's not going to move for 21 months here. And then what we know here is that then a radio transmission occurs. And because it's a radio, we know that its speed is c. And that speed of the radio transmission, there is no dilation. So if I think about the space-time diagram now, let's look at the space-time diagram. So if I look at my diagram, I'm thinking something like this here. Okay. And when I think about this thing here, I could imagine that I have the Earth moving through space-time, right? It's moving through space-time, and as it moves through space-time, what we're seeing here is that in the frame of the elephant, that rocket is actually moving through here. Right? So as it moves, what we're seeing here, what this rocket is doing is that we know that it's moving in some way that beta is not equal to 0. And in this case here, beta is equal to 0, in signifying that that's what's actually happening here. So now look what happens. There's the what? The elephant doesn't move for how much? For during the digestion period? 21 months. So when we look at this 21 months here, right, we're going to look at a rate. Let me see if I can do this right. So let me do, if I do this like this. When the rocket gets up to here, what's going to happen? It gets up to a period. I'm going to cheat here. I got to draw this parallel. Right, if I draw this parallel, I'm going to imagine that this is somewhat parallel. It gets to here. I look at this point right here. At this point, this tells me that if I measure from here to there, this is 21 months in the frame of the elephant. And then what happens? A radio signal is sent. Okay, as the radio signal is sent here, we now have a 45-degree angle. Okay, so it's got to be steeper than this guy, and I think I'm going to have to make this a little bit longer here. Let me do this. So if I come in here at 45 degrees, then what I'm seeing here is that I'm going to get an angle that gets set at 45 degrees. Now, why is that 45 degrees? Because now this is 45 degrees, right? At 45 degrees, this is what? This is V equals to C. If I look at this other one, this is V equal to C here. So I'm setting up my light cone so that this is V equals to plus C. And then on this guy over here, it's V equals to minus C. So these two guys here, so this should be, this is the radio transmission. And then over here, so when I translate back, this essentially tells me where the Earth is when the baby was born. And then, but what happens to the Earth? It continues to move. So as it continues to move up here, what you're seeing here is that this guy is, the Earth changes location here. So the beauty of this picture says that this Earth is going to be changing not only in time, but through space. So the only way I can actually talk about where to send that radio transmission is that I need to use a Lorentz transformation to go from position, let's call this A. Yeah, maybe I will use it. We're going to call this point A to go all the way to point B. I need the Lorentz transformation between those two spots. So what this picture tells me here is that there are two time elements. There's the time element 1, which is talking about the time dilated time for the birth of the elephant. And then there's a second time transmission, which is the speed of light. So when if I was to then write this whole time here, what do I mean by that? Well, I mean this here. So if I write this down, we say that there are two time periods. There's delta T1, which is the gestation period. in the S frame, right? We need to look at what does the Earth's frame actually measure, and then there's the second time, which has to do with the radio transmission. And when I look at this, then this tells me here is that the total time here, before you get the good news on Earth, is related to this. But the tricky part of this problem, this little shit right here is tricky. It's tricky because now I have to use the full-blown Lorentz transformations to calculate that time T2. Beforehand, we could look at a meter stick and look at both ends of the meter stick and simultaneously make a measurement. You cannot do that with the birth of, when the rocket takes off, because the Earth is moving simultaneously, and when the radio transmission occurs, which the Earth continues to move through that period. And that's the thing that we got to really pay attention to. So let's go do that. Let's go calculate 1 and 2 here. So here I go. So the first thing that I need to do here is that I need to calculate delta T1, and this is essentially this time here, and we want to go in and we want to go look for it now. So as we already said, the Earth measures a time dilated gestation period. Why? The elephant is moving relative to the Earth. So in the Earth's frame, we know here that delta T1 must be gamma delta T prime 1, which is the gestation period, right? So this is in the rocket frame. And so the Earth frame is then going to tell us that that has to be time dilated. So then if I do that, then gamma is 1 minus 0.75 squared. And then we know that this is 21 months. So when I calculate that, this is going to give me a time of 31.7 months when I calculate that. So I now know that the Earth is going to measure what for 21 months? It's going to measure 31.7 months. So now I have that time. So now we come to the radio transmission. So let's go look at that. So there's nothing surprising about this guy. This is the surprising one. Now we want to calculate delta T2, which is of the radio transmission. So if I look at this guy here, what am I seeing here? Well, what we've already said here is that you could see that if I sort of like slide up to this picture right here, this, ooh, that's not what I wanted. What I want here is that I want to still this image just to bring it down so it's easier to see. Because I think this is a tricky piece, okay? And what you're seeing here is this. We find here, so from the space-time diagram, the Earth has moved through both space and time. And the only way we know how to make a connection here is that means we have to use Lorentz boosts to make the calculation.
I'm not understanding why you're saying the Earth has moved through space.
Well, there's a couple ways to do this. Okay, so now if you want to do this, so how is it moving through space? Well, from the rocket frame.
Sure.
How do I look at it from the rocket frame? Well, and then if I look at the world line, the time only, right? We only want to look at the time. In that rocket frame, remember, who's sending the signals? It's the rocket. So in that frame, the Earth has actually moved from the rocket frame. So you have to know when to send that signal, right? So if I then translate this guy, we have to do that. And so the question is, by the way, maybe I should have just written this as the world line. How about if I just write this as the world line? So that way we know that we're moving through space and time. And so now we need those details right there. Where here, I was being lazy. On the left over here, the reason why I was being lazy is because we're only care about time. So if I look at the Lorentz boost, as far as the rocket frame is concerned, the elephant doesn't move. But there is a spatial component that you have to account for. Okay, so now the reason why I did that was just to answer your question. But in this frame over here, okay, so if I look at this frame, I'm going to resize this thing just so that I can write here. Oh, damn it, I'm going to mess this up here. What I'm going to do here is that I'm going to reduce this a little bit just to be right here. What I'm seeing here is that in this frame, in this picture, I only am interested in time. I'm only interested in time. So I'm going to stick to this frame over here, not this one. But this one shows you that it has to have changed location relative to the rocket. So if I do that, then why am I going to do that? So in this scenario here, what you're seeing here is that now, so then I'm going to boost, so my Lorentz boost is then going to be from the prime frame to the unprimed frame. Because if I use this frame instead, I would need those spatial locations. So now I'm only interested in time, so this tells me that this is a one-dimensional problem. And what do I mean by one-dimensional problem? Well, I know that the space here, delta x, is going to account for the change in the location here. And I know that if I do this Lorentz boost, then these guys look something like this here. Okay? So this is, of course, this is in the rocket frame, which tells me that delta x prime has to be 0 because the elephant doesn't move in this frame. But we assume that the distance, yeah, the elephant can get up and move, of course, but that distance is neglectable towards the space-time distances that you're sending the light signal. So that means I can ignore that. Whereas in the other frame, what actually happens? I get this guy here, And I can't ignore this. I can't ignore that because the earth has moved and I need to make that adjustment. Oh, I got to sneeze. It's not coming out. Thank God. Okay, now I'm good. So now what I want to do here is that if this is the case in the rocket frame, then I could then come in and I could say that this has to be gamma v delta t prime. So that change in the earth is now related to the time. And I think that's tricky. So this is telling me that the position of earth is solely due to the change in time, which I think is very counterintuitive. But that's because space-time is a mixture of space and time simultaneously. You cannot rip them apart. So if that's the case, then I could go in and calculate what that is here. And in this scenario here, what you're seeing here, oh damn, I screwed up. I screwed up big time here. Let me tell you why I screwed up. I kept thinking that the signal, note that radio transmission. How fast does the radio transmission move?
Light.
Speed of light. You know what I was doing? I was doing this in my head. I was talking about the radio transmission. And this cannot be true for the radio transmission. So I did this all wrong.
And I get it.
That means I got to start over.
What did you screw up? I get it.
I screwed up on the gestation period. This whole thing right here is absolutely wrong. Why is it wrong? For this reason right here. The earth has moved. I have to use this relationship in order to calculate. Let me see, am I doing this right? Ugh. Let me think about this for a minute. I think I'm getting myself confused. Let me drink some water and procrastinate and see if I can recover from this.
Sit back. Join the club.
Yeah, we're all just as lost as you are. Don't worry.
No. I better not be lost because I get paid to do this. So let me go back and look at this thing. This has to be right.
That it makes
That absolutely has to be right. And the reason why that has to be right is that we're only talking about the time. So I'm getting lost someplace. So this is good, okay? This is a good calculation. Since I'm gonna put this up so that you guys can get them out, and I better be as clear as I can. The radio transmission, oh, I'm good now. Okay, sorry about that. You see, Jason, that was your fault. You asked me about the other frame. No, you're just a scapegoat here. I screwed up. I see what I'm doing now. I should have started out more clearly. And the way I should have started out more clearly is this way. Is that, I even wrote radio transmission. What I should have started off was with this here. This is the more appropriate thing to start off with. what we find here is that if a radio signal always travels at the speed c, all observers measure that. So that means here that the only way I could measure the time here is to calculate this in terms of distance over time, because it's moving at a constant velocity here. So here's the thing. This, we know, this is what we're looking for. So the only way for me to calculate the time, which is what I call T2 right there, is that I need to determine delta x2 via Lorentz boost. That's the way I should have started it. And I ended up I started mixing up the other ones. So the reason why I'm calculating this distance, which I very inarticulate told you without telling you why I was doing it. And so my apologies there, but that's where I screwed up, where I didn't tell you where I was going, and I started to do calculations. And then I went like a dumbass over here and I go like, why am I even doing this? Because I wasn't clear, and it wasn't clear in my head. That's why I'm calculating this distance. So this distance, delta x2, is for what? The radio transmission. So this picture that I have right here is, you know, it is correct, but it's this distance right here that I'm actually computing when the Earth gets the signal, right? There's the transmission of the gestation period, right? We know when that occurs, and then the Earth continues to move as the radio signal is coming. So as that's the case, I have to account for that change in distance. So when I look at the Lorentz boost of the position, I could then go in and calculate what that is relative to the prime. And that's what I failed to actually tell you here. So hopefully that's a little bit more clear than me just throwing a bunch of shit up there and just saying like, hey, dumbass, how come you not get it? As you watch this dumbass instructor not figure it out either for a period of time. So that's the problem right there. So what am I going to do? Now that I have this, then that means that the radio transmission implies that this must be true here. Is then going to be delta x2 over c. And so now that I have delta x2, which is this guy right here, this is the guy that I'm going to then bring down here. Okay, so this is the position of the Earth solely due to the change in time between those two space-time events. So when I plug this in, then I'm going to get this gamma v delta t prime over c here. And if I start to sort of like plug in these numbers here, I know the gamma factor is 1.51. We know that the speed is 0.75 c. And then of course the time is this 21 months. So from the 21-month period to when it reaches Earth has to be this distance right there. And then this guy is going to be divided by c here. So when you compute this, then I'm going to get a distance of, or a time here of 23.8 months. And that's going to give me my time T2.
Hey, Carlos.
Yes.
I'm confused about why we're plugging in the 21 months from the gestation period. Aren't we trying to figure out how much time it took the radio transmission to travel? I'm confused.
Okay. So let's look back at this picture here. Relative to this CT prime frame, there's a change in distance between the Earth at this point, right? This is the point A that I'm talking about. This is the point B. So if this here is the 21 months as measured relative to the rocket, Earth continues to move this distance right here. So I need to account for this change in distance as it goes from point A to point B. Right? The Earth is not stationary. And all the other problems, the Earth was stationary. Here, the Earth continues to move relative to the rocket. So as it moves relative to the rocket, you have to account for that change in period for the Earth, from the rocket frame to where the Earth has changed. And that's what this delta X represents here.
Carlos?
If I had a sitting duck in the Earth, then I don't have to worry about it. But the Earth is not a sitting duck.
Right.
It continues to move. So relative to the rocket, this Earth is moving at some beta along that way. Now remember, those arrows don't mean anything here, right? These are just little side things to help you, remind you that the Earth is moving from point A to point B.
Okay.
So that means if I have that time period now, then that means that the good news of the elephant blowing its trumpet here then tells you that then the total time is then the combination of these two things, and these are all relative to Earth, right? These are all relative to Earth. So if I put these numbers together here, the first one is going to be what? 31.7 plus the second one, which is 23.8. So the total is then going to be 55.5 months. And that will be the total time that occurs on Earth here. So therefore, that's the final answer for the time.
Carlos?
Yes.
I'm still confused about like the delta x2. Is delta x2 the location of Earth at the moment that the radio transmission is sent out?
Yes.
Or is it the amount of distance the Earth has moved between when the radio transmission is sent and when it's received?
Well, yes, that's the same thing as far as I'm concerned. Right?
Nah.
They're one and the same.
What?
But the thing about it is that you have to account for that with the Lorentz transformation.
But Carlos, when the radio transmission is sent out, the ship and the Earth are a certain fixed distance apart.
Right.
And then this radio transmission is just going to travel that distance. It doesn't matter that the ship is now zooming off.
Right. No, I agree.
So.
But in the rocket frame, you have to know how much it's zoomed out, or actually you don't have to, but from the Earth's frame, if you want to calculate that time, right, it depends on which frame you're at. From the rocket frame, if you want to figure out how much time it's going to take to get to the Earth, you have to know that change in distance.
Yeah, I guess if you're in the ship sitting still and the Earth is moving away, when you send your radio transmission, you have to know that it's going to travel, has to travel even further.
Yes.
Why can't we say that the Earth is stationary and the ship's moving away, and then that little bit of distance doesn't matter?
By the way, there's no preferred frame.
It seems like you're preferring the frame where the ship is stationary and the Earth is moving.
Well, and that's because
Why do we
that's
have to do that?
originally the calculation that we did for the 21 months. We assumed that the rocket was not moving, and it takes 21 months here in order to go from here to there along the time axis, so the rocket is not moving.
I mean, in that, oh gosh. In
I
that
think,
graph, it looks like the red distance axis, like the Earth is not moving on its own distance axis. It looks like it's staying stationary in space.
in this frame right here, so
In the green one you're talking
in
about.
this frame, Earth does not move. Okay?
Mhm.
In this frame, Earth is moving.
Mhm.
Both of them are equivalent. I mean, in essence, which poison do you want?
I thought we picked the poison on the left.
We did, but now, and then we can look, you see, maybe I changed my mind here, because in this frame, it looks like the Earth isn't moving. So if the Earth isn't moving, how do you calculate a change in distance? And that's essentially why I went towards this picture, to have a change in distance of the Earth in order to make that number here physical. Otherwise, if you're in this frame, you don't move. But the rocket is moving. And I thought that it would be easier conceptually to think of the Earth as moving and the rocket being stationary.
Okay. So we did use the diagram on the right.
And I jumped into this frame right here.
Carlos, where would you place the rocket in that second frame to the right? Because you
In
just
this
have the
one?
Earth.
Yeah, the rocket's right here. Right? It's right here. Right? And that rocket isn't moving. So when I look at the beta here, that's 0. And in this one here, you could see that the rocket is moving as it goes through space. By the way, I think this is a extremely hard conceptual problem. I don't think the mathematics is very hard. I don't think the mathematics is hard at all in this chapter. But I think conceptually, this is the hardest example that we will probably see in this chapter. Okay. Should I move on? I know. I mean, you can always ask me questions during office hours, right? We can definitely ask questions during office hours. So now I'm really going to challenge you conceptually. I want to talk through motion through space-time. I think this is a real challenging question here. And probably the easiest example, I want to give you an analogy first before I start talking about this. Now, the analogy is that I want you to think about vectors. And what we know about vectors here is that we could imagine that we have a coordinate system that looks like this here. And if I have a vector, let's say that it's along the y direction, and this vector here has some length of a. When I look at this vector, what we say here is that you essentially have what? You essentially have maximum y component, and you have 0 x component. And one way to actually think about this thing here is that, I mean, it's kind of obvious because it lies along the x, the y direction. But what happens if I now angle the vector A? In other words, if I come back to the same coordinate system along here, and I have the exact same vector here, and it's the exact same vector. Note that when I go and I draw the components for this thing, I now have part of it in the x direction, and I now have part of it in the y direction. And and we're so comfortable saying that, the components are just are they really being divided between the x and the y's? And the answer is absolutely not. And a really, really good analogy is that if I think about weight, most people are shocked that weight is a vector, right? If I'm on the ground here, and you're standing on a weight, let's say that this is some scale that you read, and the scale reads, let's say it reads 200 pounds, and then I go stand on an incline like this, where that's the scale again. What is the scale going to read? Is it going to read 200 pounds? The answer is no. There's a component of the weight that gets distributed in this direction called mgy, and there's a component that gets distributed in that direction, which is mgx. And the only way you get 200 pounds here, right? The only way you get 200 pounds is that if you take the mgx squared term and you take the mgy term squared term and do this, only then do you get the weight of the person. So these x and y components distributed are along different axes. Weight is truly a vector. And that's what I mean by these y and x values. Here, you're going to get maximum y component. Here, you get a distribution of mgx and mgy. And it's very common for students to just say, oh, I want the weight. I can just add these guys to actually do that. And the answer is no, you can't do that. This is not correct. You will never get that because weight is a vector.